I don't mind. Yeah, it's like a TED Talk. It's fine with me. So I started to stack these materials, and so that became kind of the new age. And even just a month ago, within the last month, yeah, I like it. Leave it. It's fine. And I won't see the sleepers. It's maybe better that way. So, even up to right now, so a month ago, this paper is actually still online. It hasn't been published on paper yet. But we're studying these very, very thin, very small materials and trying to understand their basic properties. So this has been who I am identified. So when you ask somebody outside of here, who's this Gabor guy, they'll say, oh, he's the optoelectronics guy. Right? So that's been my identity, and that's fine. But there's a lot of other things that we think about. And two of the things that we do a lot in the lab are designing new instruments. So new ways of looking at this. And I won't talk too much about this today, but I want to recognize that this is what I would say is a dangerous place where we're starting to let go of instrument design in science. And I think that's very dangerous. I think in condensed matter even, more and more commercial instruments are coming into the lab. I think that's a dangerous place. So we work very hard to push these kind of experimental limits into new regimes. But maybe more the focus of this talk, I like to understand essentially what quantum mechanics gives us when we think about new photocells, the next generation of detecting light. The reason is that quantum mechanics becomes very important in these kind of quantum confined materials. And so this is what I want to talk about, and maybe this will give you a sense of where the title comes from. But this is kind of a history of myself. I was sitting in a colloquium just like this when it was about 2010. So it was towards the end of my PhD. And I don't know if you know German, but this is a Gedanken Experiment, right? It just means a thought experiment, right? I was sitting there kind of waiting for the speaker to begin, and I thought to myself, okay, what would be the best way? I have nanotubes, and I'll show you what that means in a second, but what would be the best way to design a solar photocell that I use these interesting properties of nanomaterials? That was my thought experiment. What would be the best way? Now, if you were an engineer studying solar energy design, you would go to the National Renewable Energy Lab. And there they publish this data. This is basically the mean solar irradiance. So this is power per unit area, per unit bandwidth. So it's basically power as a function of wavelength. And they give you this data, which is averaged over a certain number of hours. This is, I think, 4 hours midday at a certain longitude and latitude. They have several different measurements of this, but it's standardized. So then you would look at this and say, okay, well, where do I want my solar cell to absorb, right? What's the best place to absorb? And just to comment on some of these features, I think the astronomers probably know this one very well. What do they call this? I think the 4,000 angstrom line, right? These features are not just random noise. These are actually absorption bands in both solar absorption and our atmospheric absorption. So this is an average intensity that things on Earth see, okay? So that's the starting point. Where do I build this solar cell? Now, the cool thing is, what can we get from these new materials? And so at the time, I'd been studying a lot of these. I would say the ideal nanomaterial photocell would have a few basic properties. First of all, high absorption efficiency. So every photon that comes nearby, I want to absorb it with almost unity efficiency, right? And there are materials that approach that. Another thing you need is efficient ways to convert that energy to charge and then move it around. So I need good wires, good ways to transfer energy, good ways to transfer charge. And then if I'm lucky, I would get some interesting quantum effects. And some of the ones that are out there are multiple electron hole pair production, so I can convert one photon into several electron hole pairs. There's a thing called FRET, so biologists know this very well, forced or resonant energy transfer. This is where you take one excitation on one molecule, and that energy can resonantly excite the molecule that it's near. And then you can even have more fancy things, right? Quantum entanglement, which is kind of the computational community's interest. And at the time, I was studying carbon nanotubes. They had all of these properties. And if you don't know what a carbon nanotube is, it's essentially a tiny little tube of carbon atoms, the diameter of which is about the same width as DNA. So we were able to, and this was even in 1998, but this was one of the contemporaries of my PhD advisor, we were able to produce solar cells out of an individual carbon nanotube. So you take this thing that's 1 million times its diameter in length, and you make a single photocell out of it. And it had a lot of interesting properties. We actually published a few papers on this. But the most interesting one, I think, of all of these nanomaterials is a thing called quantum confinement. And let me explain what that means. Most of you may know this. If I change the dimension of this material, its wave function gets squeezed. Right? When you're down at the scale of the wave function, the electron wave function gets squeezed. And what happens is, as I shrink in dimension, generically, the energy scales increase. Okay? This is basically just like particle in a box, basic beginner's quantum mechanics. If you change the dimension of the box, the energy levels, the difference between energy levels increases. It's exactly the same. This is general dimension. You choose a dimension. You could do 1 dimension, 2 dimension, 3 dimension. It's all the same story, right? It's all particle in a box, okay? Carbon nanotubes, it's a little confusing because the electron wave function wraps around a tube. So there's a slight variation there, but it comes down to diameter, which is the effective single length scale. The wave function has to match its phase when it comes around to the other side. But what it leads to is something very powerful in terms of a practical application. These are the transition wavelengths of a whole bunch of nanotubes. They used to do this. They would take millions and millions and millions of nanotubes in a vial, and they would look at their optical resonances, and they would get these charts where they probe, they just plot all of the resonance wavelengths, in this case, as a function of nanotube diameter. And what you see is that the wavelength of the transitions, these energy scales in this kind of pseudo-molecule, would increase with diameter. This was quantum confinement. It gave us a knob, and this was really exciting. So if I go back to my problem of where to absorb, everyone in the room would say, oh, well, I think you should absorb right at the top, right? That's where all the power is. So that's an easy place to look. I would shine there. I see that that's green light. It's right about 540 nanometers. And then I could go down to my little chart, and I say, oh, 540 nanometers, that's a nanotube of 0.7 nanometer diameter. Now I'm going to make a whole solar cell covering a roof with these tiny little tubes that are 0.7 nanometers that are going to absorb like crazy right where I want it. Okay? The only thing I need is then a very simple, and you'll see this schematic come back. You need something to absorb those photons, so absorb the green photons. But then you need some way to convert it to an electron that jumps somewhere else and produces work, right? Just like a heat engine. I have a hot thermal distribution, that's the solar distribution, and then I have to produce work. It has to be a heat engine. So that's the simplest photocell you can imagine, is an absorber, an electron donor pair, and then you jump into some other acceptor. Okay? So the conclusion of my Gedanken experiment was the simplest quantum solar photocell should absorb green light. And I sat there and I was kind of angry, actually. I was like, no, this has got to be wrong. Because if I look outside, I see that everything outside is green, or at least most of the plant life is green, meaning nature, for some reason, kicks out all of the light that I just said we should have been absorbing, right? That's a mess. And I figured, okay, there are two possibilities. I'm right and nature's wrong, or nature's right and I'm wrong. And I usually defer towards me not being correct. I think that's the safe experimentalist way. I figured nature knows something that I don't. And so this really bugged me. And if you go on Wikipedia, like all of us do, I almost guarantee most of you do, why is the plant green? Wikipedia pops up and it gives you this terrible answer. It says, well, chlorophyll absorbs in the red and blue parts of the spectrum and doesn't absorb in the green, and so that's not useful. Completely unsatisfactory, right? But some people stop there and like, oh, great, now I know. I can tell my friends. To me, this bothered me to no end for years. I mean, almost a decade, and it still bothers me. But the point is, yeah, plants kick out green light, but we know, one thing we know about plants, for instance, chlorophyll, is one of the most oxidative molecules in nature. Meaning, when I shine light on it, it turns into free radical oxygen, which basically tears proteins apart. Plants have developed layers and layers and layers of protection to prevent themselves from being burned by chlorophyll. Yet that's the molecule they've decided to use to basically generate power. So just to stare at this for a second, same rules that I said about the materials we were studying, quantum confinement is what gives us these energy scales. When we talk about chemistry homo-lumo gaps, the rules are basically the same. The extent of the wave function on various regions of this molecule determine its energy scales, and they give us absorption spectra that look like this. So here's a textbook absorption spectra of chlorophyll A and chlorophyll B, and there's the Wikipedia answer. They absorb there, but not in the middle. Okay? But again, this bothered me a lot because there's a whole zoo of pigments that plants could have adapted to use that cover this regime. In fact, cyanobacteria absorb right in the middle. They're yellow because they absorb all of green light. So nature's quantum photocell does not absorb green light. And I'm not the first physicist to think about this problem. This is one of the subjects with the most Nobel Prizes in chemistry, biochemistry. But physicists have thought about the problem too as far back as even earlier than 1961. I like this one a lot because he points out discussions that he had with various famous names like Schrodinger, which many of you know. What he said is something very interesting. Plants are doing something very unusual. They take this wildly disordered, very high noise solar spectrum, they take those fluctuations and they convert it into stuff. Okay? So what that meant is that if you, from the point of view of just the plant, you're producing negative entropy. You're taking something disordered and giving it order. And this was a discussion that Schrodinger had. He basically said that all of life, that's what we do. That was his definition of life, was something that had a negative entropy flux. It went from something crazy to something ordered. What George Gamow said was, well, let's be more careful. When we think about entropy, we have to think about where entropy is lost and gained from various pieces. His argument in this paper was just that, you know, the entropy increases for the solar radiation and it decreases for these plants. And he argued very simply that the temperature difference between the sun and the earth is like a heat engine. And so he looked at this as a very thermodynamic problem. And his goal in this early paper was actually to address why they're green. He didn't answer it, but he at least thought of it in a way that we like to, and this will come back, thermodynamic heat engines, right? You pump it, it goes through a cycle, produces work. And there's some other perspectives. I was chatting right before this. H.G. Wells had a very famous saying, apparently the vegetable kingdom in Mars, instead of having green for a dominant color, is of a vivid blood red tint. So we knew from observations that Mars was red. And in War of the Worlds, the Martians came after us. But his opinion was kind of an interesting one at the time, that maybe there was plant life on that planet, and it was just a different color. And this had some interesting implications, and it has been taken very seriously. This is kind of a joke in the 1890s, or at least a mystery in the 1890s. As recently as 2007, a whole bunch, if you look at this paper, there are a series of 2 papers in astrobiology that address this problem. If we are searching for life on another planet, what color will the plant life be? If there are higher organisms producing energy, what color will they be? They tried, this was like the most brute force set of papers I've ever seen. It had biologists, it had chemists, it had astronomers. They looked at every possible option, and by the end of the day, they couldn't say much because it's so complicated. I mean, just look at this one graph. There's about 30 of these graphs in these 2 papers. Very complicated problem. But what they did say is actually very simple. As photosynthesis on Earth produces the primary signatures of life, right? We would look out from the outside, we would see green stuff, we would say, oh, that's life. It should be able to be detected. And a strong focus of the search for extrasolar life, so on new planets, will probably be photosynthesis and how it interacts with the atmosphere. So the atmosphere basically determines the solar spectrum at the surface of the planet, and higher life would then tune itself to that. Now, just a quick note. If you think about human physical sensitivities to radiation in the solar spectrum, the human body is sensitive to an extremely narrow band of radiation. Right? We know the visible, we see visible light. We feel thermal radiation in the kind of IR. But outside of that, we feel nothing. Can anybody in here see X-rays? I mean, maybe Superman was one of them. Does anybody see microwaves? No. We are very narrowly sensitive to the world around us. It turns out that our sensitivity overlaps almost precisely with the solar spectrum. So there's a strong argument to be made that, in fact, we are tuned, life is tuned to the local energy source, solar spectrum. Okay? Now, you can go to another perspective, which is down at the tiny. This is where I come in. We like thinking about nanoscale things. And in 2007, about the same time as that, a very interesting discovery was made. They were shining lasers at photosystems of some bacteria, and they found that the electrons behave coherently. They act like waves, essentially, through these molecules. And this came to an interesting conclusion, which was maybe nature is using quantum mechanics. Maybe this ability to maintain coherence of a quantum wave function is giving more efficiency. And then this is where physicists really jumped in. This is what we understand well, wave functions, coherence. There were a whole bunch of papers going on at the time understanding coherence in various forms of thermodynamic heat engines. And then I'll point out this one paper. Scully in 2010 said, wait a minute. I can take this old idea. This is a dye laser. If any of you were familiar with dye lasers, it was basically a laser. You'd have a ground state that was pumped to an excited state. It would relax and then release stimulated emission. Right? This was a very famous example of what was called a quantum heat engine. There was a cycle here: photoexcite, relax, create work. And that work comes out as stimulated emission. This had been studied back in the 1950s. Scully said, why don't we use this as a model for photosynthesis? I bring in light, I reach an excited state, I convert to some other molecule, and it produces power. So this was kind of a new perspective recently in 2010. This was the perspective where we got started. But there's been a big debate. And this is, I want to be very careful. I avoided this debate. I'm basically saying, well, I don't know the answer. They asked, does it matter? Does quantumness, coherence of a wave function, actually affect the efficiency of photosynthesis? This debate's still going on, and these people are angry at each other. So my strategy was, well, forget it. Don't worry about coherence. Let's think of one more perspective. So if there are biophysicists in the room, or biologists in the room, you'll know one thing about biological systems. We say they're soft. They shake. They have fluctuations. They're dominated by fluctuations. So here's a picture of this thing called the FMO complex. It's a whole bunch of chlorophyll molecules embedded in protein. And as a physicist, when I stare at this, imagine two molecules coming near each other. I have some overlap integral of their quantum wave function. I can hop an electron from one to the other. Right? We could write that down almost exactly. And then as soon as we add fluctuations, these things are displacing. The overlap of those wave functions is now fluctuating. So in biological systems, they're not clean quantum systems like a laser. They're systems dominated by noise. So that was one of the insights. Okay, weird. Okay, we should think about how does a plant deal with all of this noise? Imagine the solar spectrum, which is also very noisy. It gets absorbed in this photocell and somehow has to produce energy from that at a very steady state. And so the question I asked was, does this electronic structure give rise to some new properties? This idea that the shape and structure, the way that electrons dance through this object, does that help in the way we think about photosynthesis? And more importantly, here's what was known about plants. It's still active, and I'll talk about this a little bit later. If too much light comes into this photocell, it has to dissipate excess energy. Right? If too much light comes in, anybody knows this. If you put a tomato plant out in the Riverside sun in midsummer, it burns. It dies very, very quickly. Basically, what's happening is you're getting too much sun. You're getting too much power. That's large spikes in the power coming in, and it needs to dissipate that energy, and it has trouble doing it. So somehow it has to convert very noisy external spectrum to something that it can use like a steady state. And that's this idea that I think of as regulation. It has to regulate a noisy world and create essentially negative entropy. Right? So here again is that simple photocell. I have an absorber that jumps to another molecule and it creates power. And if I draw this the old-fashioned way, it's a laser diagram. I pump the excited state, it relaxes, and I spit out, let's say in this case, an electron. I generate some power. And I can parameterize this. I can say there's power that comes in and there's power that goes out. Power conversion efficiency is the statement that these should be as close to each other as possible. I want the power coming out of this solar cell to be as good as the power coming in, as close to 100% as I can. And we know there are limitations to that, but that's the ideal. And you can write this down. There will be a few equations. I know the audience. You can handle equations. If you think of what this power is, it's actually very simple. It's just an absorption spectrum, so I have a narrow absorber integrated with the power that the sun's bringing. It's a very simple integral. There's an absorption band, a little Gaussian peak, and then some external spectrum. And the power out is just some steady rate that's needed to leak through the photosynthetic chain to generate sugar, for instance. So our idea of regulation was this. The energy flux coming into the system, you want it to match this output as close as possible. That's just power conversion efficiency. I want them to be as close as possible. But more importantly, the fluctuations they have to be small. If I have a giant spike of power coming into this, it's too much to match this rate. I can't meet that average output. There's too much all of a sudden. So I need a system that allows me to reduce those fluctuations internally. So let me show you how it works. Here's a generic photon energy flux. Imagine a black body spectrum. And I have a very narrow band absorber. Here's my photocell. Now the power that I get is just the integral of this narrow function and the power spectrum behind it. So here was my argument before. Let's pick the peak. Okay? Now let's say that that's perfect. Right? I'm at the perfect conditions of the solar radiation. My input is some value, and it's matching perfectly my output value. So I'm charging my batteries without heating them, slow, steady rate. And then suddenly the clouds go away, and my whole power spectrum jumps up. I start exploding my batteries, right? Things start to expand. They're spitting out battery acid. My photocell's not working well. So the only option I have is to essentially shut down. I stop absorbing when that happens. So I could imagine a little demon in there saying, okay, the sun's getting too bright, turn it off. Turn it back on, turn it off, tracking these fluctuations in the external world. And you can write this down as a very simple random walk. I have the probability of absorbing that power, the power that I get, it has to equal the output. So it's just a statement of power conversion. And when you do that, you can actually write down the fluctuations. Just some scale. Don't worry about the quantity itself, but you can write down very simply. In this photocell, the fluctuations are going to be parameterized in a simple way. Okay? Now, what we found was really weird and interesting. I glue onto this other photocell just another absorber, okay? And you might say, well, that's going to divide the overall efficiency in half. And it can, but you gain something very powerful. Here's this new laser diagram. I now have an A channel that feeds into my machine. I have a B channel that feeds into the same machine. So now I just have two channels, slightly different energies, different powers because of the spectrum behind them, and basically the same model. I have power coming in. It depends on the external flux and the integral of the absorption band. Now, if I look at this regulation condition, I make all the same arguments. This is kind of cool. I create basically a very simple random walk. The energy at some time is equal to the energy at the previous time plus some random distribution. So if I'm tracking the energy in this photocell, it's just a completely random walk, simple random walk, where the distribution has basically three choices. I take power in the A channel, I take power in from the B channel, or I do nothing and I'm just always producing work. Okay? So again, a simple random walk. This is actually kind of a finance model. If you have someone who's investing for you, they want you to have a steady rate of increase. They want the fluctuations around that rate to be small, right? They don't want volatility. So they build models like this. And here's what it looks like in our model. You have probabilities, you have effectively rates, and you have some flow of power in and out. So it's a very simple classical model of this quantum system. And we say that rather than maximizing, the photocell actually just wants to regulate. So forget about absorbing the peak of the power. It just wants to carefully regulate. Now here's how it works. This is kind of the crux of the function of this thing. If I'm absorbing at the peak and I get a big spike in power, it's no different than my previous photocell. I still have to turn something off. It's too much power. But there's a bit of a weird thing here. And this actually came from Chandra Varma. Very early on, he told me there are two interesting points in any peaked function. There's the peak and the inflection point. And it's right. That's all you need, basically, to describe any peaked function. So I move these two peaks to the inflection point, and I get something very interesting. I get a little high-low detector. One of these, if you look, the spectrum is rising very quickly. So B collects a ton of power. A collects a little bit of power. Now, if I want some average value, now I have a knob that either collects high or low. If the sun comes in and it's too bright, I go to the low power. If the sun gets dark, I go to the high power. I collect what I can. And it's just this little, again, a demon in there switching randomly between these two, trying to keep the steady rate going. And you can see that they have a big difference in power. And you could do the same thing on the other side. Right? The inflection point is where you get this kind of high-low detection. Now, just to look at this schematically, here's what it looks like. This is maybe the simplest way to view it. If I have one channel, the power coming in, here's my average. Let's say I want to get this value. And as a function of time, my power just jumps up and down. Right? I have this on-off. I have some high power and zero. Right? That's the basic way. That's switching. This is like a controller, in a sense, for your air conditioner. But now I add a second channel. I don't have a zero anymore. I never turn the machine off. I always leave it on. I just bounce around my mean value with these two powers. That's the whole function. It reduces. Can you stare at these and tell me which one has lower variance in these two distributions? It's pretty easy, right? Visually, you stare at the one on the right and you say, well, this one obviously has lower variance around the mean. The scatter around the mean is reduced. So the noise, the fluctuations are reduced. And that's what we got by introducing this second channel. So now, this is the fun part. This is an interesting toy model. It's like a little detector. There's two channels. Can we actually determine the structure of this thing, this photocell, from NREL's data. That was our goal. Let's take the average values. We now want to minimize fluctuations, and we want to see if we can reproduce the best photocell. What's the best photocell? Again, it's like my thought experiment, but a little bit more advanced. So the way we look at it is that regulation happens if we have 2 channels. It doesn't really happen if we have 1. And so you want a 2-channel photocell to do this. And so here's how it works. You take any absorbing peak. They have a few characteristics. I have 2 peaks. They have a width, right? This is some full width at half maximum. They have a split between them. So there are 2 different wavelengths. And they have some center wavelength that defines their centroid, right, their position. And all I'm going to do, this simulation that I'll show you, I just move these 2 peaks across the solar spectrum. And I ask, where is the difference in the power the biggest so that I'm robust against fluctuations? Right? And you'll see what that means in a second. If the power between the 2 of them is small, and the solar spectrum is moving in a correlated way up and down, sometimes I'm not working very hard. Sometimes I get too much power in and I'm burning things. I'm not really meeting the mean. So what I want is them to be a little bit spread out so that they always are above and below the mean at any given point in time. So again, finding this balance of meeting this output demand. And I can write that down. It's some optimization. I won't bore you with that. Okay? But here's what it looks like. Our input was real data. This was the experimentalist in me trying to do theory. Give me some data. I just plot this parameter delta U, the difference in the powers between these 2 channels, as a function of their separation. So again, these 2 peaks, they move over the spectrum, and then I spread them out a little bit and move them again. And then I make them wider, and I move them across the spectrum, and I'm maximizing this difference in power. I'm maximizing this ability to switch. Now, this is kind of a cool plot. If I look at this and I take its derivative, you get this plot. Okay? If I take the derivative of this, I'd see a little spike in the derivative where these jumps are. You see little spikes here. What it comes down to, this optimization, is basically just taking the derivative of this spectrum. It's basically picking out, if I wanted a detector that had a high and a low, the best place to be would be at these big jumps. Right here is low, right here is high. They're close together. I would get my high-low detector. But now what we did is we broadened these peaks. You know, narrow peaks are very quantum. Now we're broadening them to kind of thermal energies. And watch what happens. They pick out the same values. As they broaden and broaden and broaden and broaden, it converges to a single result. There's exactly one position that is the best, most optimal position for these 2 wavelength detectors to be. The width of these 2 is 35 nanometers, and their center wavelength is exactly determined at 400. The difference between them is about 100 nanometers across. So from that, we can actually plot an absorption spectrum. So all we did, take input data, simple model, reducing fluctuations, it spits out an absorption spectrum. From that, we can actually get energies, right? So if I wanted to go in the lab and start building this, I know exactly the energies that these absorbers would have to be. I take some molecule in the middle to collect. And if I go back to my textbook, this is kind of the most exciting part to me, was when I look back to the textbook photosynthesis chlorophyll absorption spectrum, the match is remarkably close, right? Unbelievably close, in fact. When I show people this, they're kind of shocked that it converges. This calculation basically converged to these values. And it turns out this structure actually occurs in biology. So they have chlorophyll A and B molecules coupled to xanthophylls, and it's been known since 2005 that these do something called photoprotect. They think that these were the molecular basis of this ability of plants to kind of turn on and off so that they don't burn out. And people had studied them, and they actually know very well about these structures, but they didn't quite understand the function of them. And so this is even back a little bit further. Here's what happened the last few months. And this is related in a lot of ways to our paper. It was a really interesting experiment. So one thing that happens when a plant has too much light, it turns things off, and it's at different scales, length and time scales. And it takes a while for it to recover back to normal. So this group basically said, well, let's genetically modify it so it doesn't take so long to recover. Basically what they did is reduce fluctuations. If I have a big spike that has to recover, I have a longer fluctuation over some period of time. They cut out those spikes, and they saw that crop yield went up. So they reduced fluctuations, crop yield went up. And then very recently, this was in the last couple months, They actually found the molecular basis for this, and it's an electronic system that looks exactly like this. So it's now becoming more and more clear that there's a very deep connection between the plant's ability to regulate, to control fluctuations, and its molecular and electronic structure. Okay? So this was the bottom line. Regulation basically emerged. And this model, I know it's a little bit complicated, but the point is that just by choosing the energy scales of the problem, I was able to regulate solar power by reducing fluctuations. So structure allows us to regulate. And this is maybe not so surprising in hindsight. If I show you this very quickly, see if I can. Where'd my mouse go? There it is. Here's what it really looks like when plants, this is actually taken from campus. When we think about photocells, we think that, oh, they're just sitting out in this nice sunlight, it's all steady, they're just generating power, happily generating away at the perfect amount to give us light in the room. Here's what it really looks like. Pick a point on any one of these leaves and watch what it really looks like in space and time. It's not pretty, it's not steady, it's not some nice average value. It's noisy, right? Nature is effectively noisy. So plants have come up with many different techniques to basically reduce that noise. And my argument is that greenness of plants arises because of that optimization in a noisy realm. Okay? The model that I made is completely classical with scale invariance, so you could argue lots of different ways that this is happening, but that's the basic point. Nature is attempting to create negative entropy. So we published this December of last year, and it's already generated a lot of kind of media attention, but I have to thank the people that kind of helped this come to fruition. This is an idea that I'd been cooking on for almost a decade, but it was only when I came here that I got the pieces that I needed to make it actually become real. And I have to thank my graduate student, Trevor Art, but also Dr. Barlas and Professor Vivek Aji. These are people in the department that we tried to study this problem. Moreover, this made a lot of attention. When you try to predict why plants are green, people get very excited. I still don't believe it. However, I would say that it's one of the first quantitative predictions of why it's so. We laid out in that paper a series of statements that you can basically prove or disprove in plants. Most of the people that have attempted to solve why plants are green don't do that. They kind of wave their hands. We gave them a quantitative model. So at least within a few years, we'll know if we're right or wrong. Or at least that's the hope. But this was featured in a lot of different places. Nature Nanotech, New Scientist, US DOE tweeted us, which was kind of cool. And this is just a funny side story. This magazine, Futurism, is some weird internet magazine. They said this really crazy thing. Light harvesting quantum photocells herald a new age in solar energy. So apparently our paper heralded a new age in solar energy. Whenever you read this, you should doubt this. But here's the worst part. This was a picture by a friend of mine who's a professional photographer. She took this picture for me. I said, hey, do you have beautiful pictures of green planet? Yeah, I can give you one. And then I thought, okay, well, let's put this little photocell on it. This was like the journal. They have these little pictures now. Every article has a picture. Somebody at Futurism, instead of giving that little bit of credit for nearly nothing, they went and created their own. That looks almost identical, but significantly different that they didn't have to give us any credit. This was kind of amazing to me. I thought it was hilarious. And in the parlance of our current political climate, I'll shout fake news, right? So be careful what you wish for. When you get attention, things get to be a little bit more trouble. So why do people care? Why do I care? The reason is that this little model about some little tiny photocell that sits at the bottom of the world has a lot of implications. And this is what excites me most. One of them is this search for life, astrobiology. One of the things I think you need for an exoplanetary search is correlates. You need something that correlates conditions on that planet to life occurring there. And I would say that those correlates right now are very weak. And so what I would argue is that things like this, could this idea that life is able to regulate against fluctuations, it's able to create negative entropy, is that enough to connect to properties of a planet that you would observe under inspection of slightly better observations than we have? So being able to actually see the color of life on the planet. And does this idea of regulation actually relate the exoplanetary life to a star's temperature? My argument is the reason it's green, that's the local peak that it sees within our atmosphere. If you knew the atmosphere of an exoplanet and you knew the local star's temperature distribution, you could guess from our model what color life would be on that planet. If you see life of that color, you say, wow, it's doing this, okay? But now way down to the other scale, right? This is the large scale, this is the tiny scale. Let's say I'm all wrong, right? Or at least the physics is okay, but it doesn't happen in biology. You can look at this a different way and say, well, can you imagine seeing this somewhere in biology, maybe regulating something else, whether energy or anything else? But can you actually design or slightly manipulate, and I know some people get nervous about this, but manipulate nanosystems that actually do this? And can you create a benefit? This is exactly what that paper last December showed. They manipulated the fluctuations in that system and got better crop productivity. Now granted, in that paper, towards the end, they say a lot of other terrible things that happen to the plant. But we'll ignore that for now. That's normal biology, I think, as far as I can tell. But maybe more importantly is this kind of generic realm of nanoscience where we're thinking about quantum mechanics. Can this idea of regulation be utilized for optimization, right? It was a really interesting optimization to have these two channels that regulate the flux of some parameter. And so can you use this? And I've talked to, like, Martinez, Professor Martinez was asking about this. He had a lot of interest in the model for quantum computation. I'm not sure why, I don't know where it ever went. But most importantly, I'm an experimentalist. So I've been harping on about theory for the last, whatever, half an hour. I'm actually an experimentalist. So I want to be very careful. So can we demonstrate it and how? So for the rest of this little talk, this may explain the connection to what I actually do in the lab. So going back to this thought experiment, I think what we need to do is now add one more requirement of my nanomaterial photocell. I need high absorption efficiency, I need charge transfer, I need interest in quantum effects, but now I think we should be able to regulate against fluctuations. That's an important aspect of generating power. And so important, in fact, that the solar industry knows this. They don't talk about it, but they actually do this. They have very powerful transformers that they use to convert solar fields into the grid. And they have to be very careful because they can blow up people's, electrical grids this way. So we published this in December. And again, it's a relatively simple model. You can study this pretty easily. There's two excited states. There's an intermediate machine. And around the same time, there was a paper published in the same journal. It was like within weeks of a diagram that looks almost identical, right? There are two kind of sets of absorbers. They're feeding into some intermediate level. And this happens to be in the field that I'm in, which is 2D semiconductors. This diagram that they published was the energetics of taking two atomically thin semiconductors, laying them on top of each other, and just looking at the absorption and essentially emission of that energy scale. So somewhat coincidentally, some people would argue that coincidences aren't real, but I'll say coincidentally, our model and these two schematics that I show you, the schematic of these two materials, look very similar. And let me show you what it comes from physically. This is actually very simple. If I take these two semiconductors, their confinement, they're so thin that the electrons and holes, which are positive charges, turn into little effective hydrogen atoms. And so they have very narrow resonances. These 2D materials actually absorb light like a molecule over a very narrow absorption band. Okay? So you can think of them almost as molecular absorption bands. If I have two of them, I clearly have an A and a B channel, right? I have whatever this one absorbs in and whatever this one absorbs in. What's even weirder is when they touch each other, when they're overlapping, those electrons and holes can actually be decoupled between the layers. So I can have an electron in one and a hole in the other. And this is a very low energy state. So when I have these combined systems, I get exactly this diagram that I want. I can excite A, I can excite B, I can read out on the intermediate. And so this happens to be, we were studying this in parallel for several years. I studied very kind of intrinsic physics to the single materials over the past few years with collaborators at UT Austin. But this had now an experimental system that I know, heterostructures of 2D transition metal that chalcogenize, I could start to prove this. So this is what we've been working on. And I'll give you the upfront now, we haven't proven it yet, right? We haven't seen natural regulation, but I'll highlight what we have done. So when you take these 2D materials, if anyone's in my lab, I'd be glad to show you. You take Scotch tape, and you rub it together. You basically push and pull it apart, and you get dust that happens to be atomically thin semiconductors. Every once in a while, you get a little speck of dust that is an atomically thin semiconductor. And you can take these things in a very deterministic way. We have a microscope that allows us to then layer one on top of the other. Okay? So we can create these little heterostructures exactly like we showed in that last slide. And that's what they look like. You have some bulk pieces, you have pieces of different layer thicknesses, but right where we wanted it, we have these two atomically thin membranes touching each other. And here's what it looks like. This is kind of a funny picture one of my students took. I'll credit him later, but this is a dime, and who knows who's on the dime? Come on, Roosevelt. Yeah, it's Roosevelt. So we decided to implant behind Roosevelt's ear one of our devices. And if you stare, this is the actual device from the paper. Here's the D for the Mint, I think in Denver. Down here is this tiny little device. These are kind of the big wires that we feed into this. But just to give you a sense of scale, tiny, tiny little photodetector lives down between these wires. Now remember what I showed you in the plants, kind of waving in time. What we care about is local. These photocells in plants are very, very tiny. We're now kind of working in these photodetectors at the same scale. And some of the rules apply. And that's why I think this is a very interesting direction. But I thought this was a really cool picture anyway. So here's what it looks like. Down at the bottom, I wire these things up. I create a photodetector. We can then study it like conventional transistors. And I won't get into the details too much. I'll show you some data, but I don't want you to think too hard about it. In a conventional transistor, what you can do is control the charge density on these two layers. So you can turn the devices on and off. And when you do that, I'll skip this one, when you do that, you get what every computer is based on, something that turns the flow of current on and off. And so we do that. We tune, this is the current as a function of a gate voltage, which is a local voltage in the device. And you turn it on, and now it's on. If I sweep back, I turn it off. So it's a transistor. And if I take the derivative of the log of that data, I just get a little spike. And it's basically the steepest slope. In semiconductor theory, this is the onset voltage. When I apply negative 38 volts, the device turns on. Okay, so you know something about the microscopics. And after a little bit of help from some people, and I'll again credit them at the end in electrical engineering, we can actually understand all of the energetics, or most of the energetics of the system, at least relative energy scales. And you get what is conventionally called a semiconductor heterojunction. This is very old theory, but now it requires some careful calculation because these materials are very thin. But now what we had is basically a transistor we could turn on and off. We could shoot light at it. It's on the same scale as what we care about, and we're hoping to find these different intermediate energy levels so it looks like natural regulation. It looks like photosynthesis. But what really happens is science, right? Things are surprising. So let me show you this to a semiconductor experimentalist, this is a really beautiful plot. To everyone else in the room, they're like, yeah, that's some weird data. But let me show you what this plot actually tells us. This is a very rich piece of data. This is a plot of the current in that device as a function of the voltage I apply across it. So that's kind of conventional, right? I apply a voltage, I measure current. And then this gate voltage, which is tuning effectively the charge density or the chemical potential in the device. So I have these two knobs. In semiconductor work, this is everything, these two knobs, okay? If you look at this thing, it's very low current at the bottom. It's insulating. It's very high current at the top. It's N-type. And so that transition is what I showed you before. It turns on. We know all about the charge density, how it moves, how the device turns on. If we go in these positive source drain voltages, everything looks basically normal. And I'll show it to you, and just trust me, this looks like a normal device. I measure the current as a function of source drain bias. It just is on. There's a slight curve to this line, but it's on. I get current. It's on, but it's very insulating. So very high resistance. Now as I tune my gate voltage, I start to really turn the device on. I just see that same line basically multiply. It's getting bigger. So this is exactly the function of a transistor. I have a low current state and a high current state at a given source drain bias. So very simple physics, and I'll highlight the basic process. But this is, again, in semiconductor world, what happens in the reverse bias direction is what makes most semiconductor theorists or experimentalists start to think. You basically see that in the off state, there's some current at very high voltages. As I turn my gate voltage up, the current gets very large, and then I start to see this bump, okay? This is a negative differential conductance. If I take the differential conductance, which is the slope of this line, I would see that it goes kind of the opposite direction when it goes over that bump. Now, the origin of negative differential conductance comes from all sorts of things in semiconductors. So this, we spent about 1.5 years trying to understand the origin of this little bump. And it was painful, I will admit to you. It was very painful. We came up with many models. Many of them went away. What we found in the end, I can skip this part. This is basically the simple behavior, not really so important. What we found was really interesting, and it skewed my entire plan for mimicking photosynthesis, at least for the time being. In photosynthesis, we have two processes, right? There's electrons jumping between molecules, and there's excitons, the electron-hole pair. All of the energy jumps to the molecule. So that was FRET, Forster-resonant energy transfer. Those are the two basic processes. In this particular system, we generate an electron, right? So this can be with light or with voltage or whatever. When it jumps from one layer to the other, it basically undergoes this process. It jumps into the other band structure, it relaxes its energy, and outspits another electron-hole pair. So normally it would just go through and dance the rest of the way through the device. In this case, it actually cascades, and its excess energy generates new electron-hole pairs. So it doesn't look like biology, but it actually looks like a lot of exciting results that have been going over the last, say, decade or so. And so the process, this is really cool. This is, again, I'll credit the student at the end. Here's what it looks like in 3D animation space. So an electron comes in, it hits the interface, and two come out. So track one of these, watch. Two, two, two. So basically you're fissioning electrons, right? You shoot them into this thing, they hit the interface, they cascade through the interface, and they produce a pair. Now, although this doesn't look like biology, it's actually really interesting because it means that if I photoexcite one of these electrons, I get two for the price of my one photon. I've essentially doubled the efficiency of my photodetector. So we studied that. It made some predictions, and we could actually verify these predictions. The first thing is it says that it generates a lot of extra charge in the junction. And again, looking at kind of the details of the data, this slope here, which I'll show you, this is normal. It shouldn't move. This is abnormal. This slope actually tilts. What that told us was that we were generating negative charge. Right? Again, semiconductor experiments kind of verifying this. But more importantly, we started to shoot lasers at it. So we were looking at its photovoltaic behavior, and we saw this very interesting feature. Here's the photocurrent now as a function of source-drain bias. It's on at low temperature. As I turn up the temperature, we could actually turn this process on. So you generate all of these electron-hole pairs. And we could parameterize the multiplication factor. How many electron-hole pairs do we get out based compared to our kind of when it's not happening? And you do this as a function of source-drain bias, and at very low powers, we got something like 350% efficiency. So you're getting about 3.5 electrons for the price of one that you shined in there. And this is actually really exciting. If you can tune a system like this to generate power, like in a photovoltaic, you're basically multiplying the efficiency by 3 or 4 times. And so this is a lot of excitement. And people have been studying, in fact, including myself, we've been studying processes like this to enhance the efficiency of photocell devices. But this electron-hole multiplication basically leads to a humongous enhancement of the signal, of the power conversion, ultimately, in these devices. So again, this was kind of a cool picture generated for the process, and it's actually very simple. An electron in one material gains kinetic energy, and these are actually essentially quasi-relativistic electrons, right? They live in band structures that are kind of hyperbolic. They generate another electron in the other system, and they convert that excess energy into a new excitation, right? It's like a particle creation, particle-antiparticle pair. And this was just published, again, last month in Nature Nanotech. And again, an army of people to make this happen, all from UCR. So Fatima Brati kind of was the intellectual head of this project. She was digging into the data, understanding the science behind it, alongside Max Grosnickel, who kind of built foundationally a lot of the measurements and continued working through the whole project. We had to lean a little bit on some computational work, so Roger Lake and Shanshan Su in engineering, to kind of let us understand the band structure. And again, you'll see this guy, I think, on every paper that I've published out of UCR, has this guy's face on it, which is a good thing. Vivek was very insightful in the project. But really, the thing is that all the different aspects of this project, just like any project, required all of these people, right? And I want to emphasize that. So, for instance, the artwork, the dime that you saw, that was Max's pictures. The beautiful plots, the beautiful graphs in here, that was Fatima's work, right? So when you see very nice slides, it's usually coming from one of those two, Max or Fatima. They do very good work. But again, this was featured in a lot of places. It was exciting. It had this sense that we're doing something new. For me, it was like, shoot, it's not quite the perfect system, but can we get the perfect system? And we're still excited about this for other reasons. It's going in different directions, but I haven't quite gotten that photocell that I need. So now I just finally come back to this. This is basically the direction we're going with this line of reasoning. I have a whole bunch of other projects that I'm not talking about, but at least in this line of work, I'm looking for systems that mimic this basic model. I don't particularly care about photosynthesis anymore. A lot of people are asking my opinion. I don't know that my opinion is valid or not, but I should be able to look for this type of physics, this ability to reduce fluctuations intrinsically without any active feedback in generic systems. And so this is where we're looking in this field. And just to end, I want to come back to Gamov. So he was an interesting character in general. If you read about him, he's actually a very, very interesting guy. He was a theoretical physicist and cosmologist. That's what most of us know him for. I would say he was one of the earliest pioneering biophysicists as well. He had a lot of interest in genetics, DNA. He was very close to the discoverers of DNA. And he had a very interesting quote, and this is probably my favorite thing about him. So I am just sitting and waiting, listening, and if something exciting comes, I just jump in, right? This was his quote on the origin of his interest in biology. And I appreciate this a lot because that's what I feel like. I don't know that I'm a biophysicist. I would probably argue very strongly I'm not. But when things get exciting and you have an idea or an interest in some other subject that might be relevant, I would say don't be afraid to jump in. I think this is one of the biggest fears among experts, is that we don't like to jump out of our expertise. For me, it's been a lot of fun and funding jumping out of my expertise, okay? So I would encourage you on whatever level you need, you should jump out of your expertise. And like I said, I think he was kind of a pioneer in doing that. He really wanted to understand the big problems, and that's kind of the thing that we're doing in my lab. And so finally, just to kind of remind you, these are the things that we do. You can come see the lab anytime. This is my home turf, so you're close. We're working in a lot of other directions. There's a lot of things going on. I'm not so fixed to this direction. I'm almost done with it. It's like, boring. I understand those pieces now. But there's a lot of other cool things going on that I could talk about in 4 or 5 more years. And of course, all of the people involved. There's many, many, many of them. Here's the lab. This was an old picture in 2016, and my students will know that I cut off the other part. They put my face in the clouds. It's a funny picture, but I needed the space. But of course, Professor Aji, Professor Elaine Lee at UT Austin, one of my strong collaborators, her students Ka and Joe, and Dr. Barlas, Shan Su. I think she's now a doctor too. I think she's now moved on, Dr. Su, and Professor Roger Lake in engineering. So they've all been kind of pivotal to a lot of this work. But there's been a lot of other discussions. If I went through like the acknowledgments to all of this work, there'd be 6 dozen people that I'd have to kind of acknowledge, and I can't do that right now. And then from kind of the lower half of the slide is all the important people that allow me to do what I do here. And one of the interesting ones, just to mention it, I don't understand it, but I was talking to you about this. I'm now an affiliate of the Canadian Institute of Advanced Research. I'm not Canadian, nor have I ever lived in Canada, but I went and received a small amount of funding, but it's actually a really interesting organization that studies big problems like this. Now, a lot of those papers that I showed you about photoprotection in biology, those were actually done by CFAR affiliates. This is a project that they've been working on for several years, is understanding this idea of photoprotection. And I submitted an application. It must have rang in their ear or something, and so they've asked me to join. So that's been a lot of fun. I'm looking forward to learning a lot from that community. I don't know any biology yet, so I have a lot to learn. And with that, I'll thank you for your time. Okay, so back to my, okay. So any questions for the speaker? Leonid.
This model of regulation, it implies that if you measure the spectrum of a leaf, depending on the time of the day, you should see different color. And
Yeah, sure. So okay, I think that's a great question. It turns out it's probably even more complicated than that, but one of the things that happens in leaves is there's other variations of this. For instance, here's an interesting example, and I'll get back to your question. Phototropism is the ability of a leaf. They used to think that it would track the sun, okay? What they found is that it's actually not perpendicular to the sun, it's actually tilted. It's tuning the flux, right? It's like creating the right cross-section. The leaves are actually more complicated because they absorb in layers, in stacks. So if you look at different layers of the stack, you see different basic tuning of the chlorophyll. But that idea actually supports our model in some average sense, that the plant's ability, it has the ability by tuning it through dielectric screening effectively, by putting it in different pH. It can tune the spectrum. And so our argument would be that it probably would have tuned the spectrum to get something. My argument is that it wants to regulate. Other people have other arguments. The answer is I don't know, right? We don't know. If you take the leaf, it's actually so much more complicated than that because molecules have all different local environments such that if you take their average, it looks just like what I showed you. One of the things that's related to this, though, this is a really interesting one, is seasons, for instance. So we know that in seasons, most higher green plants ditch their chlorophyll. They actually they get rid of proteins that hold them together, and they start using things like xanthophyll, yellow, oranges, all of those pigments you see. That's because those pigments are better at absorbing in the green. So when they're starving for light, so when the intensity of the light drops as it becomes fall, they're looking towards the center of the spectrum. As they're in the high season, so summer, they actually move away effectively from that center of the spectrum. So it's slightly more complicated than maybe taking a single spectrum. You have to look at it on all of these different kind of time scales. But we could try it. If I had a good plant physiologist friend, I would tell them to try it. I actually have colleagues at USC who are going to try it with bacteria just to see if a fluctuating spectrum will actually drive these things to evolve towards a certain condition. And that's kind of the first layer of example for that idea.
So in your model, how do you choose the model parameters?
So it's actually, it's relatively simple. So the average output that we chose, we always choose it to be the midpoint between the two. Okay? So meaning I have a high and a low, and I want something at the midpoint. That's exactly. So all of it is driven by the external power spectrum, right? So now I assume two very narrow Gaussians of unity absorption, which is kind of nearly true. And I say, well, let's just look at the power spectrum. So that's the real data, right? I could show you, we did it for a normal black body. It looks much nicer, reproduces the same thing. But it's just basically integrating the power. And what you're doing is you're trying to make the power in the A and the B such that if they're bouncing around, they spit out some value at the half or in the midpoint, so midway between them. And that's what we do. We kind of dance across the spectrum. And I could show you more of the details.
Kind of set yourself up for that question, knowing what we know about the atmosphere on Mars, mostly CO2, right? What color plants?
Yeah. Okay, come on, Stengel. No, I don't know. It's the problem is a good one, and I will leave it to you to think about it, right? Any other questions? What's that?
The spectrum is the same. Almost
Yeah.
all of that, those features.
You just other features from the sun. Yeah, most of them are solar, but that's details. Any other questions? Yeah.
So why physically do you want to reduce volatility? I imagine this works if you want to.
Yeah,
I
okay.
understand,
Yeah.
when
I'll show you exactly why. I brought a picture. I knew this question. I planted this question. Let me see if I can find it here. Here's why. It was the last one. Hold on. It canceled it. Here's why in real world. Okay. Well, but let me explain. So if you ever plug in your cell phone, it takes hours to charge. This has nothing to do with anything except the ability to cycle that battery some number of times. They engineer the battery to last a certain number of cycles. It's basically heat dissipation. right? If I could take your cell phone and charge it in a millisecond, and it would do this within about maybe 10 cycles or something, right? So those fluctuations, when you try to store energy, that's where they're damaging, right? So fluctuations coming into an energy storage system, like a battery, is what kills it. In plants, it's exactly the same story, just a different energy storage system. So if you ever look at the Z-scheme, all the details of photosynthesis, it has to take these electrons in from a very early absorption event and slowly and very carefully commute that energy through the system to create sugar or structure, any of that stuff. And my argument is that anytime you have too much, so a spike, a lot of that has to be dissipated because the rates of accepting that electron are not going to match the rates that it's coming in. And they actually know that. So if you measure plant leaves, they measured this a long time ago, they see infrared emission when plants are getting too much sunlight. And when it's too much, there's more infrared emission. So they're basically just spitting out infrared photons, so heat. And I think it's kind of general across the two. Here's the difference. Here's maybe the most important difference is you have to address it on some network level, meaning the plant is taking this excitation, it's going through some complicated network of energy storage. So you can kind of easily imagine, I want some average rate, and if it's too much or too little, it's not going to match well. It'll still function, but just not well. The same is true here, and maybe even a cleaner example is solar energy. So in solar energy, what happens is when we have too high of an intensity, so a big spike in the solar power coming from a cell, it has to get actually wasted before it dumps into the grid. So there's this thing called synchronicity. They have to dump it into the grid in phase and at the same amplitude to accept it. What they have to do then is have giant transformers that basically dump voltage. So it's kind of this darkly kept secret about solar energy is there's a humongous waste that happens when it's very, very sunny. They're kind of optimized at some scale. And the reason is that you actually get brownouts. So often when we get brownouts, they can come from too much solar energy. So it has this effect of pushing the whole system. Let me say it this way. It's a complex oscillator, and if you push it out of phase, that's bad. And that's the kind of, those are the two similar viewpoints on two very different applications. Yeah. Oh, go ahead.
So do you think you can artificially illuminate two different planets with a spectrum that changes this inflection point and get them different colors?
So it's a really good question. I can't because I don't do plant science, but I've talked to people, and this is what they're basically trying to do. One of the other versions of that is have light that is more fluctuating and less fluctuating. So steady light versus fluctuating. That actually has been done. And they show that plants don't do well when the fluctuations are too large. Okay? But yeah, people that I've been meeting at various places have been proposing this idea. Can you shift these things? Exactly, right. Can you shift it? And maybe. Yeah, I don't know. Yeah, okay, that's a great question too. Okay, so I haven't done this yet, and maybe Vivek can help me. You know, if I take n channels, it approaches, I think, some kind of classical limit of just having, you know, basically those channels, what they're doing is they're taking pieces of the spectrum. So if I take the whole black body, that's just like having a classical temperature. So it should eventually, you know, limit to some maximum efficiency of a heat engine. But what you can think of is, once I go to 3, so even going to 2, I cut down on some total quantum efficiency, right? The highest quantum efficiency is I get 1 photon in and it gives me 1 electron out, and that works perfectly. As soon as I divide it, I then have some phase space problems where only 1 at a time can come through at any average time period.
I guess I was wondering, does your model show that 3 doesn't work as well?
I think it would. I think it would. Yeah. We haven't pushed it, but I think it would. And also this argument that it becomes less than that. Well, maybe it regulates more strongly. It'd be probably, yeah, exactly. So that's one quantity that we haven't done. I've talked to Vivek about formalizing that. How do we even, well, this is a good question. What is the metric that tells us what efficiency means? And that's a big debate right now in the solar community. Some people argue that photosynthesis is far less efficient than solar energy production, but they don't account for the fact that plants convert themselves into stuff, right? How do you account for the fact that they're building structures? So there's some new metrics that have to be met. And we've talked about some generic ways to do that. We haven't done that yet. It's a really good question, though. How about one more? We have one more before we get kicked out of the room, and we have to let the speaker travel. Yeah, I think Gail. Is it, who? Anybody? Yeah,
better than
sure.
sun.
Yeah.
And they still sort of grow?
Yeah,
I
but
mean,
not great, right?
I don't know. I mean, maybe they don't grow as efficiently or something.
Yeah.
But we've been doing this experiment for
Yeah.
somehow indoors.
Right. So what the plant science people call this is plant fitness. That's how they quantify this. And the way they quantify it in those studies is by fruit production. So what is it? How good or how how many calories are in an apple that these trees grow? And invariably, these things are terrible compared to natural lighting. But what they gain agriculturally is a lot of other things, like pesticides and all of, they can get around it doing other things where you don't have to basically, agriculturally there are benefits to growing in artificial light. Again, going back to Laura's question, you could imagine engineering experiments doing this, and they have. I mean, I think there was a whole popular time in photosynthesis research where they were doing this. I don't know the field very well, but I think now our model might actually kind of nudge things in a certain direction. But it's a really complicated set of questions. Oh, well, that has another reason. Probably the pot that's grown outside is much better. It's just that it's been illegal, right? I don't know either. But my guess is that if the police are looking for you, you're not going to have 2 pot plants growing in your yard. Anyway, okay, I'll leave it with that classic question. Thank you.